Hi everybody, this is going to be our video for 3.3, solving quadratic functions by graphing. So our goal is to use graphs to solve quadratic functions. Before we get to that, we have to learn some terminology, more like review terminology though. So a quadratic function is a function that contains a polynomial whose highest degree is 2. So in standard form, that looks like, first off, f at x, because it's a function, and out of all of these terms here, the variable with the highest exponent is 2. That would be this one. In factored form, if I factor this equation, which we learned about in the last chapter, if I factor this equation, I get these two factors. So that's why we call it factored form. And we call it factored form because we have to factor this to get this. Now, if I expand this, and we use that by doing FOIL, which we learned about before as well, then x times x does give me x squared. So that's how I know it's going to be a quadratic function. So again, the highest degree is 2. Even though it's not 2 here, when I do expand it, it becomes x squared, so it's still quadratic. Quadratic equation is pretty much the same thing. It's just an equation that contains a polynomial whose highest degree is 2. So in standard form, it looks like the same thing, but it's just going to be equal to a specific number. In our case, it's going to be 0 a lot. In factored form, it's the same thing, just the factors again, just equal to 0. And the last thing we have to know is what is the root of an equation. So I think we've gone over this as well, but just a quick reminder, a number that when substituted for the unknown in a quadratic equation makes an equation a true statement, also known as the root of an equation, is also known as the solution. So why did we learn all that stuff before about having to find x-intercepts, and how can we apply it? So we can apply this to a lot of, some actual things in real life. We can see that for most y values in the range of a quadratic equation, there are usually two x values, and sometimes these two x values can model real things in real life. So, for example, when a ball is thrown, it might attain a certain height above the ground at 2 times. So like, if we have this football here, pretend this is a football, maybe it's on the ground, it gets kicked up in the air, it comes back down. Well, every time it's touching the ground here, we could say these are x-intercepts if I drew an axis around it. I could kind of move this axis around as well, but it might be like, well, a football, kind of basic, but this could lead to other things like flight or rocket ships, where they have to kind of calculate, well, what are the chances of this coming back down again? How can we model that? Again, this is kind of on a very basic level, but it can extend to something that complicated. Sometimes a solution to an equation has a negative component, but depending on the scope of the problem, sometimes only a positive solution is useful. So, for example, if I had something like, let's say, the question that we get a lot is like, before in the last chapter, is like if the person is on the roof of a building and then they throw a ball off the building, well, how long before the ball reaches the ground? There's a negative component here, but we don't count it because we're going to have a negative time there. That's an example where sometimes we have to have a restriction on how much, what's available for the domain here. So let's look at an example with population. So the population of a small city. Sorry, this is a bad diagram over here, so I'm just kind of blocking that. The population of a small city. So why did we learn all that stuff before about having to find x-intercepts, and how can we apply it? So we can apply this to a lot of, some actual things in real life. We can see that for most y values in the range of a quadratic equation, there are usually two x values, and sometimes these two x values can model real things in real life. So, for example, when a ball is thrown, it might attain a certain height above the ground at 2 times. So like, if we have this football here, pretend this is a football, maybe it's on the ground, it gets kicked up in the air, it comes back down. Well, every time it's touching the ground here, we could say these are x-intercepts if I drew an axis around it. I could kind of move this axis around as well, but it might be like, well, a football, kind of basic, but this could lead to other things like flight or rocket ships, where they have to kind of calculate, well, what are the chances of this coming back down again? How can we model that? Again, this is kind of on a very basic level, but it can extend to something that complicated. Sometimes a solution to an equation has a negative component, but depending on the scope of the problem, sometimes only a positive solution is useful. So, for example, if I had something like, let's say, the question that we get a lot is like, before in the last chapter, is like if the person is on the roof of a building and then they throw a ball off the building, how long before the ball reaches the ground. There's a negative component here, but we don't count it because we're going to have a negative time there. That's an example where sometimes we have to have a restriction on how much, what's available for the domain here. So let's look at an example with population. So the population of a small city. Sorry, this is a bad diagram over here, so I'm just kind of blocking that. The population of a small city. So let's break apart this last definition for the root of an equation. I know we've talked about this in class before. We've talked about how the root is also known as a solution. So just a reminder that they mean the same thing. Root, solution, and for a lot of the times for what we're learning, it's going to also represent the x-intercepts. So these all mean the same thing. So if a question asks you to find the solution or to solve, or it asks you to find the root, or it tells you to find the x-intercepts, these all mean the same thing. The first part of the equation is just a number that when substituted into an unknown, for the unknown, in a quadratic equation, it makes the equation a true statement. So as an example of that, if I have a quadratic equation like this, I know it's an equation because it equals 3 here. There's no function notation, so it's a quadratic equation. So what number can I put in for x, or what is x equal to for me to get, for this side to equal this side? Just by looking at it, if I just put, x is equal to 1, well, 1 squared plus 1 plus 1, 1 squared is just 1, so get 3 is equal to 3. So x equals 1, this quadratic equation, is the solution, because it makes this statement true, or this equation true, and it's also known as the root. And it's also, in this case, an x-intercept as well. So they all mean the same thing. And the solution just makes this true. Sorry, I just realized as well that I did forget something very important. That there is more than one root, technically. Because even though I can have 1 squared here, I also could have negative 1 squared to make this equal to 3. So we can actually say that both of these are solutions. Or both of these are roots. Or both of these are x-intercepts. So there is a whole section on problem solving that we're going to talk about, but I actually think it's better if we start with the other page, the other examples, and then we'll look at the problem solving afterwards. So we're on the second page now, looking at quadratic equations versus quadratic functions. So we're going to complete this table. There's a bunch of examples, and the zeros and the roots must be within the same row. So what we mean is when we're looking at x-intercepts, remember they should line up horizontally. And I'm actually going to start with this second example because I think it's better to look at for our equation. So this equation, if x plus 2 and x minus 1 is our factors, we're actually used to seeing these equations usually equal to what variable? Not usually, but we see a lot of it. Before we used f at x or f at x, we usually just see the letter y. But remember what we said, that roots, solutions, zeros, they're all the same as x-intercepts. And we learned in grade 9 that x-intercepts, if we want to find the x-intercept, we set y equal to 0. So that's what we do in this equation. This is why we have our equation equal to 0. It's by setting this equal to 0, I'm going to be finding my x-intercepts, which are my roots, which are also my solutions. So what I'm going to do is I want to try and isolate for x here. But I have these two brackets. So what I can do is, if I want to try and cancel one out, well, if we think about this before, if I had like 2x is equal to 4 here, what I would do to get the x by itself, divide by 2, these go away because they equal 1, so we say they cancel out, but 2 divided by 2 is just 1. And 4 divided by 2, we get 2. So we're doing the same thing here, except this is the number, or this is the letter x, and this is the number 2. So to get rid of this, we're going to divide by 2, or in this case, x minus 1. Whatever I do to this side, I have to do this side as well. So this divided by this, well, these cancel out, these equal 1. 0 divided by this is always just going to be 0. So now we have x plus 2. So now if I isolate for x, move this to the other side, x is equal to negative 2. So we can say that this is going to be a root or solution or an x-intercept. So we could also do the same thing, but what if I got rid of the x plus 2? What if I had this x plus 2, x minus 1, 0, and then I just divided both sides by x plus 2? Well, then these ones will cancel out. I'll have x minus 1 is equal to 0 because 0 divided by this will just equal 0. And then I isolate for x is equal to 1. So I have two solutions here, or two roots. So I'll always have this for my factors. But instead of me having to do this every time, what we can say is, well, if I just get each of these and just make them equal to 0 separately, and then isolate for x, then I'll have my roots. So I'm going to make this one, x plus 2, equal to 0. If I isolate for x here, I'm going to get x is equal to negative 2. If I do this for this one, x minus 1 is equal to 0. Then I isolate for x, get x equals 1. So these are going to be our roots, or solutions, or zeros, or x-intercepts. So hopefully that makes sense. I mean, this is the y, but if you're just wondering what do we need to kind of do later on, we just have to know that if I have two factors, and I can just make up two factors. If I have two factors like x plus 3, and then x minus 4 is equal to 0, well, if I just get this factor, such equal to 0, and then get this factor, make it equal to 0, and if I isolate for that x, both of these, I get my solutions, or my zeros, or my roots, or my x-intercepts. So now that I know my x-intercepts in this example here for this equation, so I'm just going to cover that back up again. Now that I know what these are, well, now we know what our x-intercepts or zeros are. So we have x equals negative 2 and x equals 1. And as an x-intercept, we can write this as negative 2, 0, and 1, 0. So then we can also graph these points, these x-intercepts. So the 1 will go here, so that's 1, 0, and at negative 2, 0, which is here. Now we also talked about in 3.2 how we can find the vertex by finding the axis of symmetry. So what I could do is add these together, divide it by 2. I'll do that down here. Negative 2 plus 1 divided by 2. I would get negative 1 over 2. So then this would be my axis of symmetry, which means that negative half, which is kind of like halfway between 0 and negative 1, like here. This will be my axis of symmetry. And if I put this back in my equation, I can get the vertex. So I'll do that in just a little bit, but I just want to go over what does this look like in factored form for our quadratic function. Luckily, this is just going to be the same as here. Then this will be x plus 2, and this will be x minus 1. So then I get my vertex. Once I solve for it, I can just put a point here. I'm just going to pause the video and solve for it. Okay, quick edit. So I just put my axis of symmetry back into my equation. So I did that here. X became this. If you want, I can rewrite that. So I found this axis of symmetry by adding these together and dividing it by 2. I got negative half to be my axis of symmetry. So I put these into my equation. As x, I get these fractions, I multiply them, and I get negative 9 over 4, which is like negative 2.25. Oops, negative 2.25 like this. So again, I just put x into my equation here. This was my x value. I got these numbers, multiply these, I get this fraction, which is negative 2.25. So my vertex will be like down here. It's a little bit above negative 2. So then we have this is going to be my graph. If we have a bit of trouble with the stuff, well, we got to review that stuff. but we can go over it again later in class. But the main thing for this lesson anyway is getting the x-intercepts or the roots or the zeros and being able to find them on the graph. So let's do it the other way now in this example, where they give us the graph and we have to find the x-intercepts or zeros. So here we see we have 1 at -1, so x equals -1, and then we have 1 at x equals 2. Kind of the opposite signs of what we had down here. So here, if I want to put this as a point, -1, 0, and 2, 0. If I want to put these into the equation, I can just, again, write these down here. Sorry, I had to do another edit so I can get back to this part of the page. So now that we have these roots here, we're going to do the opposite of what we did up here. So now we have our answers. We're going to put everything to one side. So in this case, if these are our roots, we have x equals -1, x equals 2. We'll move this back to this side. I get x plus 1. And what's on this side? Well, there's nothing left over. I moved everything there, so it's just 0. Same thing in this case. X minus 2. And nothing's left over here, so we get 0. So these will also be our factors. So this will be x plus 1 and x minus 2. So you might be kind of thinking to yourself, oh, I kind of see the pattern. If I know the roots, they're just going to be the opposite sign when they're in the brackets. That's true in this case, in these cases, sorry, but when we get fractions and stuff, then it might change a little bit. So this is the proper method we should be doing. If I know what my roots are, all I have to do is get everything to one side, and then I'll get my factors for it. And then luckily, these factors here are also the factors for our function notation, or I guess our quadratic function. So now let's see, well, if I have information here now in our quadratic function, how can I get the x-intercepts for the graph? How can I list these x-intercepts and zeros? And what does it look like in our equation? And what are the roots here? So again, these factors here are going to be the same for the ones here. Now, what are our roots? Well, this is where we set each of these brackets to 0. If I move this to the other side, I get x is equal to -4. And if I move this to the other side, I get x is equal to -2. So these are our roots. X equals -4, x equals -2. This is as coordinates. So now we can graph these. -4 and -2. And 0, because again, these are x-intercepts, so they have to be on the x-axis. They're in the same row. There's zeros because they occur at when y is equal to 0. We can think of it that way as well. If I wanted to find the vertex, I know the axis of symmetry is halfway between. In this case, it's going to be at -3, and I have to add and divide it by 2. And then I put that in here. I can just do it quick. Our axis of symmetry is equal to -3. And I could calculate that. 6 divided by 2 is -3. That's our axis of symmetry. So this is my axis of symmetry. If I put this back into the equation, I'm going to get f at -3. We're saying that x is going to be equal to -3. -3 plus 4. Sorry, I should do this substituting. So I got my equation. X plus 4, x plus 2. So now put x is equal to -3 now. That's usually what my function is, f at x. So now what happens at x equals -3? Both these x's become -3. I get 1 and I get -1. When I add these, because I have to follow BEDMAS, do the brackets first, and then I get -1. So I have a vertex at -3, -1. If you see my graph already, I made an error before. So at -3, -1, I have a vertex. So my probably going to look like this. So let's do a couple more. Well, now we have the x-intercepts are 0 as coordinates. What does this mean in terms of roots? We saw here that these are going to be the same numbers. This is going to be, in this case, -3. This will be 2. To find the factors, we'll move the -3 to the other side. So we get x plus 3. Same to this side. Positive 2 goes to this side, it becomes x minus 2. These are our factors. These will be the same factors for our quadratic function, x plus 3, x minus 2, and then we can also put the x-intercepts on the graph. So they gave us the coordinates already at -3, 0, and 2, 0. Okay, I found it anyway. Here's our vertex at, we had -half as our axis of symmetry, and then when I put this back into the equation, I got 3 3/4. Just down here, I know I did use a decimal. I'm just doing it quick, so I use a decimal. So that's why my vertex will be at -half and -15/4. So we get that. But again, the main thing is the x-intercepts. So last one, they give us the roots, and now we have to get the factors in both parts and then graph them as well. So we are going to do this. I'm going to move this 4 over to the side because we're getting everything to one side. I get -4, so x minus 4 will be one factor. Now for this one, we're going to treat this a little bit differently. I want you to think back to a question like this. If I gave you this question here, what would you do to isolate for x here? Hopefully we know to multiply by the denominator here. I multiply both sides by this, because whatever I do to one side, I have to do both sides. Well, if I multiply these, I get 2x over 2. So it will give me 8. 2 divided by 2, they cancel out, we said before, because they equal 1. Left with x is equal to 8. So I want to do the same thing here with this fraction. X is equal to 1 over 2. So I'm going to multiply both sides by the denominator. In this case, 2. Whatever I do to one side, I do to both sides. When I multiply this side, I get 2x. And then I get 1 times 2 is equal to 2. 2. These simplify to give me 1. And then I want 0 on one side. So I'm going to move this one to the other side. The side is 0. I get 2x minus 1. So this is going to be my other factor. 2x minus 1. And I'm going to multiply both sides by 2. 2x is equal to 1. Move this over, and I get 2x minus 1. And these will be my factors for this one as well. So if you see a fraction, it's basically become a fraction into a factor with like a number in front of the x. So then I get 2x minus 1. So these are my roots. I have 4, 0, and half 0. So I'd have one at 4, 0 here, and then one at half 0. And I'd have a vertex somewhere. But I think you can find the vertex on your own if you want to now. So I do have homework at the bottom here, but I do want to go back to that problem solving. Because what we're going to be doing is very similar in the problem solving to this. That's what we've been doing here the entire time. So let's take a look at that problem solving question. So why did we learn all that stuff before about having to find x-intercepts, and how can we apply it? So we can apply this to a lot of, some actual things in real life. We can see that for most y values in the range of a quadratic equation, there are usually 2 x values, and sometimes these 2 x values can model real things in real life. So, for example, when a ball is thrown, it might attain a certain height above the ground at 2 times. So like, if we have this football here, pretend this is a football, maybe it's on the ground, it gets kicked up in the air, it comes back down. Well, every time it's touching the ground here, we could say these are x-intercepts, if I drew an axis around it. I could kind of move this axis around as well, but it might be like, well, a football, kind of basic, but this could lead to other things like flight or rocket ships, where they have to kind of calculate, well, what are the chances of this coming back down again How can we model that? Again, this is kind of on a very basic level, but it can extend to something that complicated. Sometimes a solution to an equation has a negative component, but depending on the scope of the problem, sometimes only a positive solution is useful. So, for example, if I had something like, let's say, the question that we get a lot is like, before in the last chapter is like if the person is on the roof of a building and then they throw a ball off of the building, well, how long before the ball reaches the ground? There's a negative component here, but we don't count it because we're going to have a negative time there. So since we can't really have negative time, we wouldn't consider that in our scenario. So another example, well, we see our negative time here. We see another example on page 142, number 14. That's another example where we might have a negative component, but we might not actually count it for the question. So let's get to an example. This is our example for the problem solving. The population of a small city is modeled by the equation P at t is equal to 0.5t squared plus 10t plus 100, where P is the population in thousands, and t is the time in years. So just to note, they're saying how the variable t works here. When t is equal to 0, the year is 2000. This is just to note that this is not the year 0, so they're showing at the year 2000. So you can kind of guess that when t is equal to 1 maybe, our year is going to be 2001. And when t is equal to 2, you can say the year is 2002, and so on. So what was the population in 2000, and what is the name of this point on this graph? So the year 2000, well, that's what they said when t is equal to 0. So we're going to get our equation here. Always rewrite it, it's kind of good practice. It's 100. And what I'm going to do now, I would go downwards, but enough space, I'm going to go this way. I'm going to say, well, this is when t is equal to 0 in the year 2000. So t is equal to 0. I get 0.5, and all the t's are now going to be 0. 0 squared is 0, 0 times this is 0, 10 times 0 is 0, these go away, I'm left with 100. So if this was a graph, say at 0, you're just going to start at 100. So y-intercept, initial value, anything like that. This happens when x is equal to 0, so that's what it's going to look like on the graph. What is the population in the year 2002? Well, we're going to use our function equation again. And they want to know in the year 2002, so what is their t value going to be in 2002? Well, we said when t is equal to 2, we have the year 2002. Because every year represents 1 for t. So t is now going to be equal to 2. We're going to put this into our equation. I get 0.5 times 4 plus 20 plus 100. Get 2 plus 20 plus 100. I get 122. So what is the population in 2002? Therefore, population, here's my short form for population, is 122. I guess I should have a therefore statement for this one too. So therefore, population is 100. Determine in which years the population of the town was 250,000. It is easier to use a graph or algebraic method to answer this question. So I've already forgotten. The population is in thousands. This isn't 100. This is 100,000. This isn't 122. It's 122,000. If you're yelling at the computer at me, thank you. You did the right thing to remind me. But I caught it in time. So remember, these are in thousands, and it says so because these last statements kind of told me at the beginning. So which years was the population of the town? 250,000. Which means that P is going to be equal to 250 because, again, it's in thousands. I got to divide this by 1,000. I get 250. So I'm going to get my quadratic function here. I'm going to make p of t equal to 250. So 250 is equal to this. And I'll write this again without the letter p there. So this should look kind of familiar. It's almost like our factored form equation, except usually it's equal to 0. Well, I can change that. What if I just move this over here to that side so that it's 0 on that side? This minus 250. Then I can simplify this. I'm going to get minus 150. Well, now it's like this. So now what I could do is, what did we learn last chapter when it looks like this? I could try and factor. I'm actually going to try and factor this equation right now. So I have a decimal or fraction at the front. You could write it as a fraction if you wanted. So I'm just going to actually common factor just to get rid of it, because I don't want to have to deal with this decimal when I'm doing my decomposition or something. So I'm going to common factor this first. So everything gets divided by 0.5, and I bring my common factor to the front. These will cancel out. 10 divided by 0.5 will give me 20t. Negative 150 divided by 0.5, or divided by half, will give me negative 300. So now, I'm going to factor this. I still have to keep my common factor there. Now, two numbers that multiply to give negative 300 that add to give 20. So what numbers multiply to give negative 300? There are a lot of them. So this is where our skills in kind of doing this are. Again, we could use decomposition at this point. That's our easiest way, I'd say. But if you can try and figure out the two numbers that multiply to give that and add to give that, well, I can already kind of see that negative 30 and 10, pretty close, because if I multiply these, I get negative 300. If I add these, I get negative 20, so I'm going to make this positive and this negative. When I add these, this gives me 20, and these also multiply to give me negative 300. I'm going to get t plus 30 and t minus 10. So these are the years here. Now, if I set these factors equal to 0, I get t is equal to negative 30. And for this one, t is equal to 10. So when did the population reach 250,000? Well, I can't have a negative time, so we're not going to include that one. But I have t is equal to 10 as a positive number. So when t is equal to 10, the year has to be, well, 2010. So what years the population of the town was 250,000? Therefore, in the year 2010. Now, is it easier to use a graph or an algebraic method to answer this question? You could argue either. I mean, if you like graphing, you could do the graph, but I honestly think algebraically is easier, because even when we have these decimals and some things, and to make it a bit more complicated, we can still do it algebraically. But again, it's kind of up to your opinion. You could use graphing technology as well, like Desmos, to graph the equation. You can't really do that in a test, but you might encounter some things in your homework where you can make use of that. So if you need technology, you might have a calculator. I don't think anyone has one of these. I don't blame you if you don't. Just go to Desmos. You can use your computer. You can download the app on your phone, and you can help put those equations on the graph to check what your x-intercepts are. So thank you for listening to this lesson. Thanks for your time, and have a good one.